Even though all Newton's laws are beautiful, in this video we are going to focus only on Newton's third law, which is basically every action has an equal and opposite reaction. If you look at the word reaction, it has the same word action in it with a little re prefix. So it's not reaction, it's actually reaction. But the action force gets repeated, which is why it's equal in magnitude. But the repetition is not exact like in Microsoft Word, but gets reversed like a mirror. So what does this mean? It means you can never exert a force on something without getting the same force exerted back on you. It's like saying in life, you can never slap someone
Ooh, nice!
without getting slapped back.
Ooh, oh, oh! Oh, no!
But what if you are a Gandhi follower who shows his other cheek instead of slapping back? Well, even in that case, you are still slapping back while getting slapped twice, which is why the slapper's hand turns red. But even if Newton himself came back from his grave, a Gandhi follower will never accept that he actually hit back. Just the whole reason for this video, where we are going to discuss how counterintuitive Newton's third law is, how difficult it is to digest it, and how hard Newton himself would have struggled to discover it. So let's start with the perception of force. How do we perceive force? Basically, as humans, we have 6 senses like vision, hearing, touch, taste, smell, and cognition. But out of this, taste and smell, we use it only for pleasure. So these 3 senses, we use it to perceive force. For example, when I slap someone, you can see my hand moving, you can see the other person moving from the slap, you hear a huge sound, and my skin and the person's skin burns. So movement, sound, pain. These 3 clues, we get it from these 3 senses, and we use them to perceive force. But if one of these 3 clues go missing, then we stop perceiving the force. For example, in cricket, we have seen so many sixers and fours. And whenever Dhoni hits a sixer, we always talk about how hard Dhoni hit the ball. But once also, no one talks about how hard the ball hit the batsman. Because the ball hits the bat with exactly the same force as the bat hits the ball. But we never perceive this force because there is no movement from the bat. The bat never goes for a sixer like the ball. In fact, the bat continues its movement as if there was no ball in between. So basically, we lose our movement clue. Even in the case of slap, we only perceive the action force, but we never perceive the reaction force because the hand moves as if there was nothing in its way. So the same movement that helps us perceive the action forces fools us by being absent for the reaction forces. But it's not just the object receiving the force that has to move. Even the object giving force needs to move. For example, let's take a basketball player who dribbles his ball. Every time he dribbles his ball, you can clearly see that his hand is moving. But if you look at the ground, there is zero movement. But still, the ground is pushing the ball with exactly the same force. So when the basketball player dribbles his ball faster and faster, the ground is giving bigger and bigger forces. But just by looking at the ground, we can never say whether the force is increasing or decreasing. But if you look at a trampoline, you can clearly see how hard the trampoline is pushing. But not all examples are as easy as the trampoline. For example, let's say you go on a vacation catching a plane. The whole time you're on the plane, eating, sleeping, chatting, you're constantly pulling the plane back towards your home. With the same force, the plane is pushing you towards your vacation without even realizing it. Here, all 3 clues go missing and we have no way to perceive the force. All the examples that I showed so far were about the movement clue. But if you look at sound, sound cannot be produced without movement. So even sound goes missing most of the times. For example, when you're holding your phone while watching this video, you're actually pushing on your phone, otherwise the phone will fall down. But there is no sound except mine. But what about our last sense, touch? Well, if you take a spring and try to stretch it, you can easily experience Newton's third law using your sense of touch. Because the harder and harder you stretch the spring, the harder and harder the spring pulls back on you. Action equal to reaction. But let's say you pull the spring so hard that the spring breaks. Now you have 2 springs in your hand, and let's say you try to move one of those springs. Even in this case, when you're moving the spring, you're giving action forces in order to move the spring, and the spring is giving back exactly equal reaction forces. But you're no longer able to feel them like when you're stretching a spring. So what's happening? Why do we feel a pulling force when we stretch a spring, but nothing when we move a spring? Well, say you're standing on a weighing machine. The number that shows up on the scale is basically the force with which Earth is pulling on you. But we never feel these forces unless we sit or stand for long hours and develop an ache in our body. This is because our sense of touch perceives pressure and not force. Since pressure is equal to force by area, only when you step on a thorn, The same Earth's forces you suddenly start to realize because the same force is now acting over a smaller surface area. Similarly, even in the case of springs, when you were moving a spring, the force required was in the range of 5 to 10 newtons. But when you were stretching a spring, the forces involved are in the range of 100 to 200 newtons. So in the pressure equation, the force itself reduced and the pressure reduced. So moving a spring as stretching a spring is the same thing as standing on the ground as standing on a thorn. Our sense of touch only measures great pressures. But whenever I show this picture to someone, people often confuse these two forces to be Newton's third law because the forces are opposite in nature and equal in magnitude. But if you look at the forces, one is gravity, which is given by the earth, and the other is normal or contact force given by the ground. And since ground is part of the earth, both forces are exerted by earth on the object. So the actual Newton's third law is the object pushes and pulls earth with N and mg, and earth pushes and pulls the object with mg and N. But why does earth both push as well as pull? Like a toxic couple who message each other, I love you and I hate you on the same day. Well, since contact force exists only if there is contact, when the object is in the air, there is only gravity. But as soon as the object is on the ground, the contact forces appear and cancel out the gravity. So when the object is in the air, there's a strong pulling force, but when the object is on the ground, there is zero net force. So basically, the earth behaves exactly like a spring, where only when the object is pulled away, the spring starts to pull. And when the object is together, there is zero pull. And just like an object starts to oscillate in a spring, a free-falling object starts to bounce on earth. But we never see our big blue planet as a spring. That is because all our senses are screwed up and we are left with the last hope, cognition. So you can never see, hear or feel force, you can only reason with force. So it's like the Tamil proverb, Kannal pappadu poi, Kadal keppadu poi, Thira visaripade mei. Meaning what you hear and what you see are both false and what you reason out is the truth. So now that we have started to reason, let's go back to all the examples we have seen so far and try to figure out why in each of those cases the reaction force was never able to move the object. For example, let's say there is an object M on a frictionless surface and you're trying to move the object with an acceleration A with your hand. Now, the physics of the object M is very simple. It gets a force from the hand F, and because of that, it gets an acceleration A due to Newton's second law, F equal to ma. But if you look at the hand, in order to keep pushing the object M, the hand should also keep moving with an acceleration A. So if we take mass of hand to be m, for simplicity's sake, then just like the object, the hand also needs to be pushed with the force F, since it has the exact same mass and acceleration as the object. But since there's a reaction force from the object, action equal to reaction, the body has to push the hand with double the force, where 1F is used to cancel the reaction force and 1F is used to move the hand. But if the body is doubling the force it exerts on the hand, then because of the contact between the hand and the object, some of that force will get transferred to the object. But if the action force on the object increases, then the reaction force on the hand will increase. And if the reaction force increases, then the body will have to triple its force. So if you keep on continuing this loop of logic, then even an infinite amount of force won't be able to move the object because you will be met with an equal and opposite infinite reaction. So like how Joker says, it will be a case of an unstoppable force meeting an immovable object. So what's happening here? We're clearly able to move all the objects around us. So what's going on? To dig deeper, let's isolate the hand from the rest of the body and try to understand what's going on. So let's say this is our hand and I make a cut at the wrist. Now there are two objects, M and our palm, that the rest of our body must push together. So a new diagram will be a shorter hand and two objects M2 and M1 that we are trying to push together with the same acceleration A. Again, the physics for M1 is simple. It receives a force F1 and gets an acceleration A due to Newton's second law F1 equal to M1A. But for our palm M2, you have a reaction force from the object F1 and an action force from our body F2. So the force equation would be F2 minus F1 equal to M2A. Since F2 is both compensating as well as pushing the object. But since we know F1 equal to M1A, if you substitute that here, then F2 equal to M1 plus M2A. So what has happened? Basically, our body has become shorter, but the force that the body has to give has become bigger. So just like the previous example, where the hand had to push the object, Now, a shorter hand has to push a bigger object. And using that principle, we can now make the cut anywhere in our hand, say our forearm, elbow, bicep, or tricep. And everywhere, we know exactly how much force the upper body exerts on the lower body, because for any cut I, Fi is equal to mass of lower body plus mass of object into A. So if we now make a million cuts in our hand, then our hand will look exactly like a train with millions of coaches, where every coach has the same mass M and every coach is connected to each other. So if we use the formula we just derived to understand how the forces keep increasing inside the train, then the force to move the first coach is simply Ma. Force to move the second coach becomes 2 Ma. For the third coach, 3 Ma. And if you look at the reaction forces, they keep continuously increasing as we go along the train. So if there was no Newton's third law, then every coach simply needs a force Ma to move the entire train with an acceleration A. But because every action gets an equal reaction, the action force on the second coach needs to increase to compensate the reaction force. But if the action increases, then the reaction force increases. And if the reaction force increases, then the action force needs to again increase. So our intuition of action-reaction pairs continuously increasing in a loop was correct. But where we went wrong is, we only noticed one action-reaction pair, when in fact, there were millions and millions of action-reaction pairs between every two cells in our body that we never notice whenever we kick a ball or move an object. So every reaction force from all the passengers in a plane gets swallowed by the plane, because every reaction force in an action-reaction pair is swallowed by the action force of the next action-reaction pair. And the counterintuitive thing is, the farther and farther away from the object we are pushing, the higher and higher the forces inside our body keep increasing. But do they grow infinitely? Of course not. In the case of moving an object, the movement stops at our shoulder, so the forces grow up to our shoulder. But in the case of rowing, since the rotational movement stops at our core takes the maximum load. This is why in gym, they keep lecturing about core strength, even though we only see our hands or legs working at the point of contact. So now that we are good at detecting opposing forces, there's still the question of equality. According to Newton's third law, when a huge elephant crushes a small ant in the jungle, the ant gives back the exact same force the elephant is using to kill it while it's dying. But this is very hard to accept, because we all know that in a boxing match, the bigger guy punches harder than the smaller guy. And it's not just the jungle. Every kind of force known to mankind obeys Newton's third law. For example, in gravity, a huge planet attracts a small satellite with the same force the satellite pulls the Earth with. And the same is true even for electricity and magnetism. Your small fridge magnet pulls the Earth's magnetic core with the same force the magnetic core pulls the magnet with. So the reason why this is very difficult for us to digest is, we judge forces by the accelerations they produce. For example, if we want to find the strongest person in our group, we play this game where the strongest person is able to make the puck go the farthest. But you can easily cheat this game by replacing the puck with a heavier puck right before the stronger guy hits it. Because now the puck won't cross our mark even though the guy is stronger than us. And the reason why this works is, according to Newton's second law, force is proportional to acceleration only if the mass is constant. So in a game of seesaw, if we take the mass and acceleration to be the heights of these players, then given a force F, when mass increases, the acceleration must automatically decrease to make the product still be equal to the force.
Wow! My God!
So even though a 5-gram magnet magnetically attracts a 500 kg magnet with the exact same force, the accelerations produced are completely different. So even though the 5-gram magnet races across the floor to meet the other magnet, the 500 kg magnet hardly moves at all. And even though in boxing matches, the smaller guy is not capable of giving bigger forces, he's still mirroring every force the bigger guy gives through Newton's third law. So even if the smaller guy gets beaten to a pulp, the match should still end up in a draw, because the forces exchanged are equal. But that never happens, because just like the accelerations were different for equal forces, even pain experienced are completely different for completely equal forces. This is because not all locations are built equally in the human body, which is why a kickboxer uses his shin bone, knee bone, knuckles, and elbow bone in order to attack opponents. While the weak spots in our body, like eyes, nose, mouth, throat, temples, and diaphragm, is desperately protected by a boxer using his hands. Every boxer pulls his chin in to protect his throat, raises his gloves to protect his temples, and rotates his hip just in time to protect his entire torso using the shin bones of his hands. So just like hockey and ice hockey, if boxing was conducted in ice, where there's no friction, then both players will start playing in opposite directions from just one punch. Which is why if boxing was conducted in space, then we don't even need referees to stop the fight, where instead of tying the ropes around the rings, we can tie the ropes on the players so that they don't fly off and stop the fight. So now that we can finally reason about opposing forces that we cannot see and accept them to be equal even though it doesn't feel that way, let's try to look at some of the famous examples of Newton's third law and try to make sense of it. So if we look at the water hose pipe from the fire engine as our first example, then just like the gun, when water comes out of the pipe, there's a recoil in the pipe making action equal to reaction. But if you look at it deeper, the super speed water that has the power to push even a 1000 kg car in its way surprisingly pulls on the pipe without pushing it. So shouldn't friction from the super speed water push on the walls of the pipe in the direction of the flow instead of pulling it? So let's try to understand using an example. Let's say I take a hose pipe and I stick a bubble gum inside it. Now, when I switch on the motor to increase the speed of the water inside the pipe, the bubble gum will get pushed in the direction of the water, or will it get pulled towards the motor? Well, our common sense says that when you drop a stone inside a river, the stone will get pushed in the direction of the water instead of getting pulled back. In order to understand what's going on, we need to first look at balloons. Since balloons are made up of rubber, a balloon is nothing but a 3D rubber band, where not just in one axis, but in every axis, the balloon behaves like a rubber band. So when you blow air into your balloon, you're basically stretching thousands and thousands of rubber bands all at the same time. And since a rubber band is nothing but a stretched spring, the balloon is going to resist the stretch by pushing back on you. So the force you feel whenever you pump air into your car is the same force you feel when you cock your gun or draw a bow, since tires are nothing but cylindrical balloons. So in the movie Up, when an entire house was being pulled up by balloons, we completely forgot the fact that some of our own houses are running on road using those same balloons. But not all tires are balloons. Like tubeless tires, there are also airless tires, like the ones in our desk, chair, fridge, washing machine, and shopping carts. And it's thanks to these airless tires that we don't have to pump air into our study desk every once a week. And shopping malls manage thousands of shopping carts without the pumping headache. So why don't our own cars use airless tires? Is it because of the heavy weight? No. Bullock carts have carried tons of weights using airless tires. So is it because of the high speeds? No. Trains travel faster than cars using airless tires. So the real reason is sound. When you pump air into your tires, it minimizes the contact with the ground and therefore reduces the noise. But trains have chosen the other side of the trade-off, where they learn to live with the sound to get rid of the pumping headache. So coming back to balloons, these stretched rubber bands / springs are constantly pushing on the air to get back to their original shape. But the air is sadly trapped inside by the very same balloon that's trying to kick it outside. So if we open the mouth, the balloon immediately pushes the air outside through that opening to shrink back to its original shape. So if we now zoom in, you can clearly see the balloon shrinking towards the right to generate an action force on the air. But if we zoom out, you can clearly see the balloon flying towards the left due to the reaction force it is getting in return from the air. So when the entire balloon moved to the left, the balloon itself actually moved to the right. This dual movement of both left and right, although seems weird, is actually more common than you think. Whenever we walk, our feet goes backwards in order to generate an action force on the ground, while our body goes forwards because of the reaction force it's getting back from the ground. But there's a small flaw in this logic. Instead of releasing the mouth, if we create an opening by pricking the balloon with a needle, then instead of flying like before, the balloon now suddenly explodes. So why does a mouth hole helps the balloon fly while a pinhole causes the balloon to explode? Well, the answer to that is when we prick a balloon, the small hole that we introduce turns into a huge tear that leaves the balloon in two pieces. Which is exactly like the Sivakarthikeyan comedy where Satish, his friend, only places a scissor on the dress while his friend drags it across the entire shirt, tearing it into two pieces. So what our needle created was an unstable hole while the balloon's mouth is a stable one. This difference in stability is the same reason why some rockets fly while others explode. So if we now take the same balloon and stick a sellotape on it, then pricking the balloon won't cause it to explode because the sellotape is catching all the different balloon pieces together, preventing them from tearing apart. So if we now go back to our hose pipe, then let's say I seal the pipe before switching on the motor. Then just like a pressure cooker that has its lid on and flame on, the pressure is going to build inside the pipe since the lid's on and the motor's on. So all the pressure is now going to stretch our rubber pipe just like a balloon. And just like before, if we now open the pipe's mouth partially, then just like the balloon, the pipe's going to push all the water out through that opening to get back to its original shape. So the whole time we were wondering why the water was pulling on the pipe, we completely forgot to ask ourselves why the pipe was pushing on the water in the first place. Because the water's pull was a reaction force in response to the pipe's action force. So when water pushed on the car, it was an action force for which the car replied back with a reaction force that slowed down the water. But when the water was pulling on the pipe, it was a response to the pipe's action force which was speeding up the water. So when you pour water from your normal household garden hose pipe, the water there never pulls on your pipe because the pipe's not pushing on the water. So just like rowing, you need to push the water and initiate Newton's third law for the water to react back and pull on you. So suppose there's a paper boat lying right in front of you in the lake, then the same body of water that pushes on the paper boat in the direction of the water pulls on your boat in the opposite direction. But when we dig into the mechanics of the hose pipe, things get very weird. For example, the stretched pipe being a spring pushes on the water this way to get back to its original shape. And the water as a response pushes back in the opposite direction. But how did these north-south forces produce a movement in the east-west direction? You can see the same weirdness everywhere with liquids and gases. For example, when you're bursting water balloons by stamping on them, the stamp produces forces in the north-south direction where the ground pushes the balloon with normal force and you push the balloon with your force. But somehow the balloon moves in the east-west direction. So how does vector A plus vector B, instead of cancelling and becoming 0, equate to vector C plus vector D? And in the case of pouring water on the floor, the vectors C and D are not just in one dimension, but in every axis possible, 360 degrees. So the reason why the physics breaks is, when it comes to liquids and gases, we are not talking about one single object, but millions and millions of molecules. In order to understand, we need to look at guns. Everywhere we go on the internet, people say the recoil is because of Newton's third law, action equal to reaction, where the trigger of the gun hits the bullet and the bullet hits back. But if you remove the bullet and check the power of the trigger in an empty gun, then the force is not even enough to even kill a mosquito. So what's happening here? Why does the bullet fly at supersonic speeds and kills a person because of this stupid force? Well, the answer is gunpowder. Every bullet cartridge is made up of three parts: the bullet, the gunpowder, and the primer, where the primer and the trigger together create a mechanical spark just like your gas stove lighter. So when the gunpowder catches fire, there is a huge explosion inside the gun, and since all explosions are symmetric, the explosion pushes both the gun and the bullet with equal forces.
Fire.
So it's not because of Newton's third law that we get a recoil. Even though the gun and the bullet hit each other, that force is so small that we never realize it, which is why we never get a recoil whenever we light our stove. So the actual recoil that we actually see is due to the explosion we create inside the gun. And since all explosions are symmetric in nature, the gun and the bullet receive exactly equal forces. But since every explosion is 3D, the gun doesn't just receive a force in one dimension, but in every dimension possible as well. But since all the forces get cancelled, the gun only gets pushed back as a recoil. So what happened to Newton's third law? In order to break down an explosion and see what's happening, we need to first understand fire and exactly how and when fire turns into explosion. So basically, fire breaks out whenever fuel reacts with the atmosphere, where the carbon in the fuel reacts with the oxygen in the air to produce carbon dioxide. So basically, the solid state carbon in the fuel turns into gaseous state carbon, the smoke. And whenever this combustion happens in open space, we get fire. And when the same combustion happens in closed space, we get an explosion. Why? Because even our atmosphere, just like our planet Earth, behaves exactly like a spring. So when you take a pocket of air and try to compress it, the more and more you compress, the harder and harder the air will push back. This is why an empty water bottle is harder to crush when the cap is still on. So when you burn gunpowder inside a huge test tube filled with water, the small space that the carbon occupies in its solid state after detonation suddenly occupies the entire test tube in its gaseous state. And if you are wondering how the fuel burnt inside water where there is no oxygen, it's because just like a rocket that carries both a fuel tank and an oxygen tank to keep burning in outer space where there is no atmosphere, the gunpowder also, which is a mixture of many different chemicals, carries its own supply of oxygen. So coming back to our explosion, when you conduct the combustion in an airtight container, you're basically forcing this huge volume of air to compress itself and occupy a small space such as this. So just like a compressed spring, the air pushes back and tears apart the container. So even in the balloon example, we only talked about how the balloon was a 3D rubber band, but never talked about how the air inside was a 3D spring. So if the balloon was a spring that got stretched, then the air inside is a spring that got compressed. So if we forget about the balloon for a second and focus only on the air inside, then as we force more and more air inside the balloon, the air starts to feel more and more compressed. So air inside starts to push back on the balloon from all directions. But because of symmetry, all the forces get cancelled and the net force on the balloon becomes zero. But as soon as you open the balloon, the symmetry is intact in the north-south direction but breaks in the east-west direction. Because the top half cancels with the bottom half, but the left side goes unbalanced due to a missing force on the right side. So the balloon is also in an explosion like the gun, where both got pushed to one side, while forces in all other directions got cancelled. So if we now apply the same explosion theory to hose pipes, then we no longer need to worry about Newton's third law or care about how the action-reaction forces exactly work. So if we completely forget about the pipe and the pipe's forces and only focus on the water, then when we open the pipe, we can clearly see water being a compressed spring expanding out, causing the symmetry to break and producing an unbalanced force on the pipe system like the balloon, and therefore causing the pipe to thrash around, getting caught on one side of this water explosion. So all famous Newton's law examples like firing a gun, flying a rocket, flying a balloon, pressure cooker, or pressure hose pipe can all be reduced to a problem of a gas or liquid being compressed heavily and the spring expanding back violently, giving the impression of an explosion, and also at the same time expanding symmetrically to give the illusion of Newton's third law. So Newton's law has nothing to do with the symmetric behavior of our nature. So did all of internet make a huge mistake by misunderstanding nature's symmetry for Newton's third law? No. Instead, Newton's third law explains the symmetric behavior of our nature. So when you burst a cracker during Diwali, the reason why the rocket blasts so beautifully and so symmetrically in the sky is because of Newton's third law. In order to understand how, we need to look at conservation of momentum, where force is equal to ma, momentum is equal to mv, where force is simply checking how the momentum is changing with respect to time. So what is conservation of momentum? In order to understand, we need to first look at center of mass. We all know what the center is. If I give you 4 points, You can simply eyeball and tell me where the center is. But to say the same mathematically, we need to first plot those 4 points in a number line and then take the average of those 4 points to find the center, which is basically sum of points by number of points. But in life, no one is fair or centered. We all carry some bias. We all judge a book by its cover, and we all discriminate on meritless basis. So mathematically, this bias is introduced using weights. So if I give you a different set of numbers, say some negative and some positive, whose center is at the origin, then by introducing bias or weights only to the positive numbers, say I multiply all of them by 2, then we can move the center partially towards the positive side. But since 4 into 2 means 4 gets added twice, the number of participants in the numerator increases, and so the denominator that carries the count of the participants must also increase. So even though the weights increase both the numerator and the denominator, the center of mass still ends up moving towards the positive side because the weights increase the numerator more than the denominator. This kind of biasing, if we do it with probability, then it's called machine learning, where the same average is called neuron based on the neural network of our brain. But the same biasing, if you do it in physics using mass, then it's called center of mass. So let's say we take a carrom board and we want to find the center of these coins. So our system includes all the coins and doesn't include the striker. But we only know how to find the center when the points are lying on the number line. So let's take only the x coordinates and find the center on the x-axis, and similarly do the same on the y-axis to calculate two centers, which when we plot xcm, ycm becomes the center of these coins. But like I said, the averages are not simple averages of the positions. They are weighted averages where every position is weighted by the mass of each coin. And since the multiplications increase the number of participants in the numerator, the denominator must also increase to reflect the same. Now, these two equations can also be written using one equation if we use vector form. Because even in vector addition, the x components and y components are always added separately. So if we bring the mass to the other side and take the sum of masses to be capital M, then our center of mass also looks exactly like the coins in our system. The only difference being the center of mass is a mathematical point that floats in space carrying no meaning and acts as if all the mass was concentrated at that point. So if the player now hits the striker, then all the positions of all the coins will change, and so will the center of mass. So if we differentiate the above equation, then all the position vectors will change into velocities, and you will see that all the individual momentums of all the coins is connected to the momentum of the center of mass. And if you differentiate again, the velocities turn into acceleration, and since F equal to ma, these are nothing but forces that every individual coin is experiencing. And if you sum up the forces to get net force, then you again get F equal to ma, meaning the center of mass experiences every force that each of these coins experience. So if I hit the first coin this way and third coin that way, and the coins start moving in those directions, the center of mass experiencing both forces moves in the resultant direction. Because for this example, the equation sums up both forces and the net force determines the movement of the center of mass. So just like our brain, which has pain sensors everywhere in our body to experience forces anywhere in our skin, the center of mass also experiences accelerations from every single force acting anywhere in our system. But our human brain is not good at detecting internal injuries. This is why our left arm pains when we get a heart attack in our chest. Doctors call this radiating pain, where the body's ability to locate the force is poor for internal injuries but excellent for external trauma. So similarly, even our center of mass only responds to external forces and completely ignores internal forces. For example, when a striker hits a coin, this is an external force because the striker was never included in the system. So when the coin moves, the center of mass also moves, feeling the force. But when two coins collide, the collision forces that the coins experience is never detected by the center of mass. And the reason for that is Newton's third law. You see, with internal forces, when the coins hit each other, both feel the exact same force due to Newton's third law. And since the forces are opposite in nature, when one coin feels the force F, the other coin feels the force minus F. And when you sum up all the forces for the center of mass equation, then the internal forces get cancelled and the center of mass doesn't feel anything. But when the striker hit the coin, the reaction force on the striker never gets counted in the center of mass equation, and the center of mass feels only the action force and starts moving. So when there are no external forces and all forces are internal, then due to Newton's third law, in the center of mass equation, all the forces will get cancelled and the center of mass will receive zero acceleration. So if ACM is equal to 0, then derivative of velocity is also 0, which means dVCM is 0, meaning velocity of the center of mass doesn't change at all. So when a bomb explodes, the center of mass of the bomb, which has zero velocity to begin with, should have zero velocity even after the explosion. Why? Because the chemical reaction that explodes the bomb also follows Newton's third law. So all the internal forces will cancel and the center of mass will not gain any velocity, which means if VCM is 0, then the derivative of the position is also 0, meaning drCM is 0, and RCM, the position of the center of mass, shouldn't change at all. So before and after, the center of mass should stay at the exact same point, even though every particle in the system is flying everywhere. This is possible only if the explosion is symmetric. So when one 5 kg stone when flying towards the right, two stones, one 2 kg and one 3 kg, should go flying towards the left, so that the average of the stones doesn't move anywhere. So when a spring expanded in both directions equally, or when a Diwali cracker exploded in all directions symmetrically, everywhere the system was trying not to move the center of mass. So the whole time we were debunking all famous Newton's law examples to be a simple case of symmetry, we never realized the symmetry inside Newton's law itself that's responsible for making the entire universe both beautiful as well as symmetric. So to humor oneself, one could even think that the human body is symmetric because the embryo didn't want the center of mass to move. But that's not true because we experience external forces all the time. So the point is, the story that Newton sat under a tree, saw an apple fall, and then wrote the entire physics of gravity, understanding how stars revolve, is so ridiculous that even if Newton was alive today, then he would be jealous of the Newton we write in our stories, because if only he was that smart, then he could have written all of physics in just one afternoon and enjoyed the rest of his life partying with his girlfriend.